So we're marching through the hydrologic cycle. Got like a couple more weeks, and then we're gonna switch and start talking about high temperature geochemistry. But today we're gonna finish talking about estuaries. We're talking specifically about particles, things that happen on particle surfaces, and what that impact is in the estuary sediments. And we'll have kind of a segue and we'll start talking about the oceans. And we'll also talk about the oceans next week. So this reading for chapter 15 in white really more goes with this. And the stuff that was the reading for last time, which is Burner and Burner chapter 7, is where you'll see some discussion of this kind of stuff. Not a lot of detail. Unfortunately, the stuff that we're going to talk about today is mostly not in textbooks. I'm not exactly sure why. But anyway, maybe one day I'll write a textbook. So, and these first few slides were ones that were in the packet for last time. I just copied them over. But, and so if you recall, we were talking about particles. We're talking about the way things stick to particles and the various reasons why they stick. And flocculation and the formation of sedimentary signatures and signatures in the water column that make estuaries be this transition zone from the freshwater part of the hydrosphere to the saltwater part of the hydrosphere. And these changes, they're not only due to particles, but they are heavily influenced. And so if you think for a second about all kinds of particles that we have various kinds of organic matter, we have various kinds of weathering products of silicate rock from terrestrial watersheds. We have just small broken up pieces of kind of primitive minerals, unweathered things, plagioclase, olivine coming out of rocks, for instance, here. We have particles that come from human activities, various things that wash off of roadways and so forth. And the list goes on and on. And so as you can imagine, the chemicals that are associated with those particles are going to be different depending on what the particle is, right? Some particles really love to have certain things. Other particles, have different things stuck to them. From the perspective of dissolved solutes, where they're just looking for something to interact with, they may have a variety of choices. And those particles may not behave exactly the same in an estuary. Some of them may be more dense, some of them may settle more differently. Some of them get into the sediments and may transform in the sediments. We talked about copper and organic rich particles last time. And so that if those organic rich particles get into the sediments and microorganisms start to decompose those particles, then stuff's going to change, right? Whereas if something is connected to, let's say, a clay mineral that goes into the sediments, it doesn't really care if the conditions of pH or PE change in a sediment. Then something that's stuck to one of those particles is going to have a different fate in the sediment column. So one of the things that people like to look at are what they call metal associations, right? Which is, we have a bunch of metals, some of them are in the water, some of them are with the particles. How can we tell how well stuck are they onto the particles and what particles are they stuck onto? And one of the simplest ways of doing this is through the virtues of chemistry, where we take a sequence of successively stronger and different chemical reagents and we expose particles to them, and then we see what comes off, right? We kind of go through this step sequence of, what happens. We call that sequential extraction. And this is a table. These are example processes. Don't try to memorize it or anything, but there's some stuff in here that we have talked about before, and so we're going to spend a moment thinking about them. And to some extent, you would choose which ones of these things to do on the basis of, what do you have? Maybe you look up in a microscope at your particles. There are other processes that can be done too, but these are the phases that these various steps address. So things that are absorbed through or are via cation exchange, they basically get salted off, right? You basically present a solution to that material that has so much of some other ion that we don't expect to find that much of naturally, for instance, barium. So we populate all the CEC sites on that clay, for instance, with barium, and all the other stuff gets pushed off. We just out equilibrate, and then we measure everything that came off. So we've got things for detrital and autogenic phases. Can someone define those two terms for me? Does anyone know what those mean? The detrital, like detritus, is stuff that's just been carried along from some place, we don't know where, and then deposited. Most sediments are detrital. Authigenic means created in place. So, and we're going to talk about some authigenic phases in a moment. They are things that, let's say, conditions change as you're going down in a sediment column, such that a chemical that was soluble becomes insoluble and starts to make little crystals of something. That's called authigenic phase. Okay. So then phases that are hydrogenous, phases that can be reduced, right? Like iron or manganese particles, things, and that can be broken apart into sort of like moderately and easily reduced carbonate minerals, organics, and those organics can be broken down into different things. Reduced organics, humic and fulvic acids, as we talked about before, solid organic material, and then finally the detrital silicates. The stuff is like what would be for us the particles of the salt rock that are coming down the watershed. They're the hardest to dissolve. The stuff that's in them tends to sort of stay in them. And these kind of primary mineral phases tend to not stick very much stuff onto their surface. They're just kind of like the extra stuff that flows down the river and contributes to sedimentation and perhaps the process of flocculation and all that stuff. But so you often have seen a lot of states they don't even bother with this, right? Because this stuff doesn't really impact the water quality per se. It's just going to settle out. And what these chemical treatments are things that are basically designed to address one or another thing, like salting off or oxidizing the reduced phases, but not touching anything else in the solution, right? And so there's a bit of trial and error that goes on with this kind of chemistry, you know, because whatever happens to be in your mix of particles in your particular place that you're studying, you might have to do this different times. You know, some of these treatments may actually attack multiple kinds of phases. So in any event, this is what's called successive extraction, and I'm going to show you some results of that now. So this is some successive extraction work done on two things, some particles in Los Angeles Harbor and some particles in the Rhine River. And I've color-coded them to kind of make stuff stand out for different phases in the particle content. They see much different elements and how they are distributed. And in this, you know, part of the graph, it says what the process was, right up here, the list of things. Whereas down in the bottom, it tells you what the phases are, right? So, like for instance, here it says residual extraction, and here it says detritus. It's the same thing. It's the last thing on the list. It's this stuff down here. That's why I color coded it to try and make it easier to follow. And so what you see is that first off, the particles in these two settings are really different, right? Just look at, for instance, the element manganese. Most of it's residual in LA. Most of it is not residual as part of this iron manganese hydroxides in the Rhine River. Okay, and some elements are more similar. Like let's take a look at chromium. It's pretty similar. But the key thing I want you to see is that, for instance, if you were one of these easy to perturb contaminant, largely contaminant elements like cadmium or zinc or lead, your distribution looks really different than if you're something that's more common in the environment naturally, like iron, nickel, or cobalt. Right? So these guys here, like for instance, this kind of orange or yellowy hachured thing is humates, right? So the organic materials. This light yellow thing is exchangeable cations. This blue thing is carbonates. So look at that with zinc. It likes carbonates. So if we happen to be in a situation where, let's say our carbonate sediment was coming down, we got into the sediments, and something started to happen to make the environment really acidic, this stuff might dissolve and liberate its zinc. Can anyone think of something that makes the environment acidic? Acid rain, yeah, totally. Another thing that can happen in sediments, if there's a lot of organic matter, is a lot of respiration. And stuff that happens in sediments where the pore water space is really small can have a big effect on the chemistry, much bigger than if the same process were happening up in the water column, because volumetrically there's a lot less. So if you have an organic rich sediment that is isolated to the extent that fluid doesn't really flow through it very well, then respiration of the organic matter there by microorganisms can decompose, it can lower the pH and decompose carbonates, for instance. So, you know, like I say, both of these environments are contaminated. right? And as we talked about last time, it is hard to find watersheds in most of the places where people live that don't have significant impact on their particulate load in the rivers and estuaries that those rivers feed into, and therefore into the coastal zone from human activity. I have some examples from Hawaii, which is basically some studies that were done basically in the 90s and 2000s of particles looking along various watersheds. Some of them, a lot of detail in the kind of Manoa watershed, leading down into the sort of whatever Makiki, Macaulay / Hulu area, and then into the Alawai Canal. The interesting thing about the Alawai Canal is it's an artificial estuary that was dredged and built in the I think it was finished in 1917 or 1920, something like that. It wasn't here before. This was just like a bog. It was a wetland. And so, and this thing was designed, you can see it on the map how weird it looks, right? It's got this weird bend. The worst part about its design is that whereas the Manoa Stream and Palolo Stream kind of have a confluence over kind of right over there where it always smells really bad because of the sewage treatment facility. But in any event, they've also taken Makiki Stream, which used to flow into the ocean on its own into the area where the boat harbor is, and they rerouted it to come in here. What it does is it carries a load of sediments that deposit near the mouth. It makes a sill. And then, when we talked about sills last time, that restrict the flushing of water back and forth. So the water behind that sill, especially deeper than the depth of the pile of sediments, doesn't flush very well and can go anoxic back here. It's also accumulating the particles of these urban watersheds. And so that's kind of an interesting confluence of, you know, particulates that have some natural component and some not natural component, and conditions in the water that we wouldn't necessarily naturally find in a tropical estuary. And so this is kind of why people are interested in this. That, you know, plus the fact that we know when this was made, and we know, you know, when the sediments started to accumulate in there. And it has been dredged more than once. And I mean, interestingly enough, the sediments that get dredged out of here are so laden with heavy metals that they can't just be dumped right offshore, right? They need to be treated as hazardous waste. Okay, so this is some pictures of a study, an early study that was published in 2000. Each one of these dots are places where samples were taken. And we're just going to look at that now. So this slide and the next slide are the same thing. They're sequential extractions. There's only 4 steps in this sequence, not the full table that I showed you before. You got the exchangeable ions, the reducible ions, the oxidizable ions, and the residual, right? So the one thing that's kind of missed in here is organics as a separate phase. But they're considered, if you hit them with the strong at producing and oxidizing agents, you can decompose organics, humics, and have them release their metals. So what you see is for these elements, all of which are common in our rocks, aluminum, iron, nickel, cobalt, the bulk of the particles have these black bars, which is the residual dissolution, right? That's the small particles of rock. And then you also see a substantial amount of stuff in the reducible phase. That's, for us, largely organic matter. There isn't a huge amount of other sort of dissolved constituent or particulate constituent that's reducible here. And then a little bit, you know, in this textured pattern. But the thing that's so interesting is very little of most of these elements are in the exchangeable, you know, fraction. The stuff that's just sitting on clays that can come on and off. The one exception being cobalt has a little bit of a white bar. Now, if we go to the next set of 4 elements, their graphs look a lot different, right? And these are elements that we don't really find in the rock. It's not that there's none, it's just that they're not very common. We see copper, manganese, zinc, and lead. And you can see for yourself that some of them, like for instance, zinc, is split kind of roughly 1/3, you know, exchangeable, 1/3 reducible, and 1/3 detrital. But I'm speaking in broad generalities. Whereas the lead is almost all part of the reducible fraction. And so we talked about processes that happen in sediments that might change the pH. What about processes that change the PE? Right? Something that consumes oxygen, right? So if we have organic rich sediments that have a lot of respiration, the PE is going to go down. So what happens to reducible phases when the PE goes down? They get reduced. And again, they liberate the metals they're associated with. So we might expect to find high concentrations of lead in the water associated with the sediments that are being reduced in the back part of Alawai Canal, for instance, as the ultimate fate of these particles. All these particles were collected in Manoa. They haven't reached the estuary yet. This is just, I don't know why I have a second figure of the plot, but this is basically now a summary from that same study, looking at a bunch of different elements and how they partition into the various phases. And so again, titanium, which is dominated by the rock composition, is found entirely in the reducible phase. Things like barium and lead, almost none of it's found that way, right? Excuse me, I should say detrital. The black is the residual, or detrital, and this half-Sheward pattern is the residual. And this is basically showing you how lead evolves along the river basin as you flow downstream. How much of it is, you know, in the various phases relative to the water. Okay, so what you see is that as you go, outlet means like into Alawai Canal or the ocean, there's more, it's accumulating. This water is flowing down the gradient along the 6 kilometer gradient. It's accumulating lead. It's a messy plot, and it varies during the year, right? And storm runoff and all that kind of stuff. But they say this is the way in which people use these kinds of measurements to understand. So this is just now the connection of, you know, that watershed comes down, drains into the Alawai Canal. It has a couple pictures of the canal being built, and people have looked in the canal as well. There's actually kind of continual active monitoring process here. So there's a bunch of stations, B, M, G, H, M, G, and this is where the Makiki stream comes in or creates that sill. And so what you see is when you go along the canal, this is distance from the harbor mouth, this is the depth, right, and in meters. And so there's this point where, ooh, it gets only a meter deep, right? And at low tide, sometimes some sediment actually pokes out there. And so what that does is it takes the back basin, everything behind there, and it limits the amount of water that can flow back and forth. If you recall, I mentioned that terminal moraines in fjords are a way to block the flow of water so that we don't get typical estuarine flow patterns, and that's kind of similar here. So fresh water can flow out across the top, but seawater infiltration and tidal mixing is blocked by having a sill. So it makes the residence time of water back here go way up, and we see impacts of that, including the fact that it oftentimes smells. So here's just another example from the island of Oahu, which is looking at sediment supply into the Pearl Harbor estuary system. It's a compound estuary, multiple rivers and streams feed into it. And there are varying land use practices as we go from over here towards the Evo Plain, which at the time of this study was 100% agricultural, as was this, right? I mean, you know, you have white coffee and stuff, but for the most part, agricultural, residential, and then turning into sort of a light industrial plus Navy on this side of Pearl Harbor, and then, you know, but including the uplands. So you might anticipate, you're going to get different particles coming in over here than over here, and that is true. That's what's been found. And the not only the nature of the particles, but what's stuck to the particles varies as well. And this is just kind of a detailed map of kind of configuration of the harbor. This was like in 1920, before a whole lot of stuff was done. The Navy was there, but pretty much only over here, right? This is kind of the zone in between where like the Arizona Memorial and all that stuff is. Most of the rest of the harbor was still pretty much unimpacted by human activities. And then, you know, over time, right, you start to have the airfield, Hickam, and a lot more hardening of the shoreline and rerouting of water flows. You're starting to see ships out here. So this is like circa 1990. And again, this transition might cause us to anticipate, not only do we see differences spatially because of the different land use practices in the watersheds, but also temporally because of the changes in the way land use practices around the harbor have changed in time. So that if you were to do sediment cores, you might expect to see different things as you go down as things have evolved. And at some point you reach the point where the kind of pre-industrial point where you're just looking at Hawaiian activity, the native Hawaiian activities, and then you can even go beyond that and find the point where there weren't humans living here in the islands. And all that stuff is recorded in the sediment and it shows us the differences and the impacts that humans have had. So unfortunately, I don't have any fancy graphics, but these are two tables, this slide and the next slide. There are a bunch of stations. You have to kind of read through them on your own, but each station, each location has a surface water and a bottom water, right? And the bottom water is going to tell you something, some combination of what's happening with the mixing coming in from the ocean and the tidal forcing, as well as what might be desorbing from particles at the sediment water interface or being stripped out of the water by processes that are exporting things from the water to the sediments. And so you can, there's things like the temperature, which will tell us the degree of stratification, the pH, the dissolved oxygen. On this slide, we've got phosphate and nitrate, right? And as you could imagine, the locations that are fed in the harbor that are being fed by primarily agricultural sites have higher concentrations of nutrients, and they're much higher in the surface water than in the bottom water, presumably because they're being supplied in the runoff and the fresh water is floating on top of the salt water, as in most estuaries, and some of that stuff is being consumed by fertilizing photosynthesis so that it's not as free nitrate phosphate as high of a concentration when we go down to the bottom water. Like you can see this location, ammonia changes from 14 to 2.5. So most of it's being consumed. These are a bunch of heavy metals, a little bit more complicated, but it's the same thing. For some reason, the table says surface and deep, whereas the other table says surface and bottom. I don't know. If I were the editor, I would have caught that. But in any event, I don't know if this means the same exact thing or not, but I assume it does. And again, you'll see differences at some sites between what you find in the surface water. Here's cadmium, almost none of it in the surface water, and a lot of it, more than a factor of 10 in the deep water. Again, this is largely due to either absorption or desorption processes happening on particles. Okay, so now the final thing, and this is a picture I showed you last time. I just want to remind you of this, a ternary diagram of what happens to a whole host of chemical elements in a generic model. This is a model where stuff stuck onto various kinds of particles is exposed to freshwater and seawater. And what happens when we go from the freshwater model, we find a lot of these elements are, in a variety of forms. Some of them are complex, some of them are adsorbed on a particle, some of them are free ions. But when we stick them into salt water, most of the adsorbed metals unadsorb. It's a process we call salting off. It's largely, they are competing with the huge quantity of sodium and magnesium, especially, but to a lesser extent, other ions in seawater too, cations, that outcompete them for the sorption sites, so they basically desorb. And some of them go into water as free ions, and some of them go into water as complexes, but they're not on the particles. So again, if you can take the particles in either the last two examples, the Olawai Canal or the Pearl Harbor, and stick them out into the ocean, whether it's because we dredged them or whether we got a big storm that basically flushed a bunch of stuff into the coastal zone, one of the things that's going to happen is that the chemicals that are stuck onto the particles are going to desorb. And that gives them the opportunity, whether they have various fates in that environment, but one of the fates is to be bioaccumulated into the base of the food web by organisms that then can introduce those chemicals into, for instance, the food chain if people eat reef fishes or something like that, or seabirds or anything of that ilk. This happens whether we're talking about an environment with natural particles or an environment with anthropogenic impacts. It just happens to different degrees because we tend to enhance the concentrations significantly of some of these elements. And this is just an example of a couple, again, particle streams that have been exposed to seawater, okay? Exposed to seawater for 4 weeks, like approximately a month. This is taking the particle and diluting it, in this case, 1 to 5 with seawater, and this sewage effluent. And this is taking particles that come down the Los Angeles River and mixing it with water and then waiting and seeing, well, what happens? And here's the salting off effect, right? These are concentrations. Some of these concentrations are incredibly high, copper and zinc, kind of reflecting the processes through which sewage manages to accumulate a lot of the legacy chemicals of human activity. And this is already treated, right? This is treated sewage. This is not like raw sewage, obviously. That would be really like gross, but I'm sure people have done it. But this is the amount of the metal that got released in a month, right? So you can see here, cadmium, almost 100% of the cadmium stuck on those particles was released. Cadmium wasn't measured in this case, but some of these elements, you know, lead and copper, for instance, you can see how much of them come off. Zinc. So a significant quantity of metals will salt off. So now we've talked about sort of a flow path from freshwater into estuaries and into the coastal zone. And we've seen that the particles that come down in the water, think back to the, for instance, the Rhine River example we talked about last time. The water changes composition as it flows through there. The particle content changes composition, and the processes that cause this kind of continual redistribution of elements from either being stuck to particles or not change as a function of a whole bunch of different parameters that are likely site-specific and even seasonal, right? So it's not like we expect to find the same concentration of chemicals in the nearshore environment here all year. They may vary, or for instance, with rainflow patterns, with particle content delivery changing from kind of dry to wet season, all that kind of thing. Like once you enter into a wet season in a place that has one, and you have a few heavy rains, then the particles coming off the watershed pretty much washed all the easy to wash contaminant particles away. Start to get more terrigenous particles. But so as you can imagine, it's a relatively complicated set of processes, and natural ecosystems have developed over millennia or longer ways to kind of adapt the organisms that live there, the way the ecosystem functions, where we find different populations of things and how the land develops or the seabed develops and how that might change throughout the year is something that makes different environments sort of unique as per all those estuary pictures we looked at last time. But then when you superimpose the kind of amphisphere and human practices on it, sometimes it can cause problems, and more so than other times. It's complicated. So I just want one final thing I want to talk about on this kind of topic with particles is treated sewage in coastal zone cities such as ours almost always take their treated effluent, they pump it offshore, okay? And they do it because there aren't a lot of places to put the treated sewage here on land, although on Maui, they do some injection well for some of their treated sewage. And it ends up basically just sort of seeping out into the coastal zone anyway. But as you can see from this, it's piped offshore below the thermocline. Remember, we've got that gradient and conditions that take us from the surface water to the deeper water, so that when these effluent, and they're usually distributed, they have pipes that have various kind of diffuser mechanisms on them, so it also doesn't come out in one spot. It's kind of mixing and so forth. But because there's a lot of respiration going on in there, even after it's been treated, there's still a lot of organic matter in there. So we have gas and we have a little bit of heat. And so oftentimes we find these particles rising up as a plume. Maybe they aren't able to breach the the density contrast between warm, low density water sitting above the thermocline and below. They'll rise up, they'll mix, they'll entrain with other seawater, and the plume will get dilute, spread out, and some of the heavier particles will fall out. This whole process of kind of migrating these particles in the water column allows them to salt off chemicals as per this process. Okay, and so this is an example, for instance, of what you see in the Santa Monica Basin, which is off of Los Angeles Harbor and Los Angeles. This is depth in the waters of 40 meters, so it's not that deep, but it's not that shallow either. And the depth of their sewage outfall is like a little bit less than 20 meters deep. So there's a bunch of different scales on here. This first one is light transmission, right? Something we call nephelometry, which just tells us, well, how many particles, how turbid is the water? We do that by passing light through a cell and looking at how much light, we know how much we've given it, how much comes to a detector. And so what we see is that the particle light transmission, which is down here, so this is low, a lot of particles, high, not so many particles. At the depth of the plume, it's really low, right? Light transmission, a lot of particles, obviously. And at that location, we look at the concentration of these three elements, lead and copper and zinc. We have really high concentrations in the water because they're salting off the particles. And then above and below that, we see less of an effect, but not a complete effect. And part of it is we see the concentrations coming back up in your bottom water because secondarily, some of the particles that settle down to the seabed continue to lose some of their fraction. Okay, so now we're going to spend the rest of the time of our estuary topic to talk about, well, what happens in the sediments, right? And if you think about an estuary, we looked at those examples last time, and we walk from the river part of the estuary out to the ocean, and we take samples in the sediment. The first thing we're going to expect to see is a transition from purely terrigenous sediments to mixed sediments to sediments that are marine sediments as we go all the way out to the mouth of the estuary. And how much we find in different proportions depends on the conditions in that particular estuary. But if you recall, we looked at the city of Hamburg and the river on the Rhine River feeding around it, and we saw that the tides can come upriver something like 10, 15 kilometers and affect the kind of stability and composition of the various particulate loads and absorbed ions, and so it changes what's in the water, what's in the sediment, and everything else. So it can be a really long distance. And so then imagine you're going down with time, and let's say you're in an environment that's very stable, like every year is exactly the same, then we expect to see the same thing as we go down. But places where it changes a lot, they have wet years or dry years, or places where human activities have really changed the watershed, for instance, in the last 50 years or 100 years, we expect to see a transition as we go down the sediments. So there are sedimentation rate variations and sediment composition variations that have to do with what's happening physically in our estuaries. Now, superimpose on that stuff like the redox ladder. We got a lot of organic rich sediments, and they're coming down and they're being deposited in the stack. And as we go down, we're going to see a transition to different steps along the redox ladder as well, so that the sediments that may be constant with depth or changing depending on conditions will also experience different conditions that develop within the sediments. This is where that distinction between detrital phases and authigenic phases is so important. Authigenic phases, things that are produced right there on in situ, reflect the conditions in the sediment, whereas detrital phases reflect the conditions of transport and deposition. Does that make sense? Okay. So the kinds of things that we find in the sediments and estuaries represent kind of time-integrated processes. Sort of, even though we've been talking about anthropogenic impact, I just want to sort of take your mind out of that. Just think about what happens naturally in watersheds. We have terrestrial weathering, right? The breakdown of rock and the transport. We've got photosynthesis and respiration. It's happening on the land. It's happening in the water. And then we have, the things that are superimposed on by this. And again, we have various ways, certain chemicals that we know, like for instance, cadmium and lead, are pretty much always coming from human activities in most settings. You can find environments where we have ores of those that are rich in those elements where naturally we can find high concentrations. But we have ways of separating out the human impact from the natural. So, as I mentioned, each can change as we go down with depth into sediments. Estuarine sediments, in particular, because they have such a high concentration of organic rich material that comes down from the terrestrial watershed, estuarine sediments tend to be very organic rich, which means we tend to find them being anoxic within just a couple centimeters, right? 1 inch is 2.5 centimeters of the interface with the water, right? So as soon as we get down into the sediments, conditions change, they're reducing. And we start to go down the redox line. And so the more easily reducible phases like the nitrates and the manganese, we're going to see that reduction happening more shallow. We have to go deeper to start to see the iron transition and the sulfide transition and maybe even methanogenesis. But when you think about this chemically, you've got sediments that, except for maybe the top skin, like icing on the cake, the bulk of the sediments are reduced and the water that's over them is oxidized. That's a big contrast. We call that a chemical front. And we can find other conditions that are chemical fronts as well. Whenever you have two materials next to each other that are different with a sharp interface, it's called a chemical front. And one of the things that happens in nature when we have big sharp contrasts is diffusion tries to take place to smooth out those differences. And diffusion can, to some extent, cause a rearrangement of chemicals to try and minimize the chemical front, but they rarely, completely erase it, to the extent that we can still see it. And in this case, it's kind of emphasized the chemical front is from consumption of oxygen because of respiration-mediated breakdown of DOC. This is done by microorganisms. So these are two step profiles from the water into the sediment of two cases. A chemical that is really soluble in the water, soluble when it's oxidized, and insoluble when it's reduced. So the concentration is high here. This is a concentration scale A increasing in that direction, B increasing in that direction. And another chemical that is insoluble when the conditions are oxidized and soluble when they're reduced. Okay? And so there's a strong chemical contrast that we talked about somewhere between like the upper 2 to 10 centimeters of the sediment. We go from being oxidized to reduced, which I've kind of mimicked here. And instead of seeing like a sharp boundary, we see this gradient. That gradient is what's called a diffusion profile. We can see it when we look at the chemical profiles of elements in pore waters. But what's interesting about these kinds of conditions is that diffusion tries to erase this difference, and that's what's causing this profile. And so in the case where something is high in the water and low in the sediments, right, diffusion is going to try to increase the concentration in the sediments. We're going to get a flux of this chemical A from the water into the sediment. That's the flux is by diffusion, okay? So flux, I've just written here as F, and we can measure and infer things about the flux by looking at the gradient of A, which is the change in A with depth, which is just X. That's what dAdx is. Right? It's just a gradient. Now, if we're in the case which tends to be more problematic, where we have something that's not soluble when it's oxidized, but soluble when it's reduced, that stuff can flux back out. So if you recall last time I made a comment about how I don't eat anything that lives in the sediment water interface, oysters, clams, etc. This is the reason. Especially any food that comes from any location where there's human activities in the upland environment. Just think about all those particles that we just talked about. So it's no longer just fresh materials, it's stuff that's loaded up with cadmium and zinc and all sorts of other stuff. Gets down here in the sediments, gets liberated, comes up, and you got a bunch of filter feeders living right there like, what do I want to eat? I don't care. I just suck in water and take whatever's there. And it happens to be full of a bunch of stuff that's fluxing out of the sediment. So just think about that. Next time you have some oysters. I've written down here something called Fick's law. Fick's law is a simple statement of how much diffusion happens, how much do we predict? And it basically says that the flux, this thing F, is basically a constant of diffusion, which is a characteristic of the sediments, right? Like how porous are they? What temperature is it? When we're in water, right? If we were in a different medium, like if somehow we were on a planet where we didn't have water, we had liquid nitrogen or something else, then these diffusion constants would be different. We'll talk about diffusion in silicate melts, for instance. The rate of diffusion is a lot slower in a dissolved basaltic melt than it is in water. But in any event, these are constants that people have measured. And the flux is basically this constant times this gradient, right? And so as we can see here, the sign of the flux is going to be different in this case, in this case. It's all relative to how we define what is positive X. right? The positive x, if x is increasing with depth, then this gradient goes down with x, and this gradient goes up with x, and so we're going to have a positive or negative sign here, and it's going to give us a different sense of flow. So now let's just think about some common elements that we have in the water that are either soluble or not as they change from oxidized to reduced. Water column sediments. For instance, manganese and iron, these are part of the redox ladder. We know that they're oxidized forms, they're not soluble. They come down as particulates. Get into the sediments where it gets reducing, redox ladder happens, they get soluble. So they're going to flux out. They're going to be in this category here. They start to dissolve. Got a bunch of other stuff that is soluble when it's oxidized, it becomes insoluble when it's reduced. Some examples of things like uranium, chromium, and rhenium. So they are in this category. They're soluble, they're high here. As soon as we get into reducing conditions, they become insoluble, so their concentration goes down, so we flux stuff out of the water into the sediments. Okay, so now I have an example. It's kind of a complicated plot, but this is an estuary in Europe, in Western Germany. And so this is depth centimeters, in centimeters into the sediment. And there's a couple of things. There's, this scale is in percent. So for all the iron and manganese, which is shown here in a couple forms, which I'll talk about in a second, they're all measured on this scale. And up here is EH. And so if someone stuck an EH probe in and they measured the EH at different depths, and they see, ooh, look, all of a sudden at about 15 or so, 17 centimeters depth, it changes. Right, so ooh, there's something going on. Decomposition of organic matter is lowered the EH, right? So we've started down our redox ladder. So now let's look at the chemicals. So the open symbols are stuff that's dissolved in the water. Okay, so here we are in the upper part of the water column, sediment column, very little manganese or iron. As they're oxidized, the environment is oxidized and they're insoluble. But as soon as we get below this change in EH, boom, their concentration goes up. It doesn't go up as a step function, it's got that curved shape. That curved shape comes from this, right? They're showing this pattern. So we already know by looking at it, there's some kind of fluid flow going on, because it doesn't just go like this and that. It has this upward bend to it, which is diffusion. Does that make sense? Yeah.
Which one was the oxidized and reduced again? The open circle or the?
Open is oxidized.
Okay.
And closed is reduced.
Okay.
So now if you look in the, or I should say, open is dissolved and closed is solid.
Okay.
That's what the distinction is. So if we look at the closed symbols, they're these guys here, right? We see a big spike in the sediments. And it's above this horizon. But what's happening here, and then it goes back down, is that at this point in time, this snapshot, we've got a change in EH as we go down. We're starting to oxidize our particles and see concentration increasing in the sediment with depth in the pore water. We have a flux of these elements up because diffusion is trying to erase that gradient. And as soon as the water that has the dissolved constituent comes up across this EH boundary, where the conditions are oxidized again, these things come back out of solution. So we get this very enriched layer of iron and manganese in the particles, and this is largely from what we call octogenic phase production. This is stuff that's happening right there and then, not something, it's not because, oh, you know, whatever, 100 years ago, there were a bunch of these particles coming down and they made a layer. It's because we see it associated with this depth change in this dissolved constituent. We know how diffusion and fluxes work. We know that this water comes up across this boundary. It gets to a certain point where the conditions are such that the dissolved stuff reprecipitates out. Now, if you like kind of imagine, add a time dimension to this, over time, we're going to keep adding a little bit more sediment to the top here. Like think about every century. We add a little more sediment, all these gradients move up, right? You have new oxidized material up here. And so this band, at some point, like in the future, this variation in EH may happen shallower than this in sediments. And then we redissolve this stuff. And so this band can keep getting richer and richer as we move in time. If those sediments have sat there undisturbed for a millennium, then we can see the integrated effect of more addition, even though if it doesn't sit in the same location, it keeps migrating up. Okay, so that is just a text version of what I just said. So now I want to look a little bit in kind of an early detailed study of estuarine conditions. This is, North Carolina, looking along a graded river into an estuary and measuring what's in the sediment and what's in the water. Okay? And so there's basically 4 stations that they've included in the paper, stations F, P, S, and C, which is a little bit hard to see, but here's station F, it's way up here, way up in from the coast. This is kilometers, so I don't know what that is, but 15, 20 kilometers. As the winding river goes, there's station P, there is station S, and there's station C. So none of these are in the open ocean. C is like, kind of the mouth of the main part of the estuary. The rest of these are up in the river. However, with tidal forcing and all that kind of stuff, we can see the incursion of saltwater relatively far up, and as we'll see in a second, it can have an impact on what we see in the sediments, as we talked about last time. So 2 things that, for instance, vary along here. Some of the graphics are not great in this paper, so I've kind of redrawn some of them. Here's one that just shows you pH versus salinity. As we talked about last time, pH in most of the freshwater part of the hydrologic cycle is acidic. pH in the ocean is basic. So as we go from here out to here, it goes from being acidic, it stays acidic, but eventually when we get to the ocean, it's going to go basic, right? But so pH 7, which is, I don't know, on this kind of, I forgot to put tick marks here, but it'll be something like here. This is close to neutral, this is close to acidic. So it's going to be a change there. There's also the salinity. The salinity tells us the relative proportion of seawater and fresh water at the time we sampled up in the water column. So this is, I should say, these are measurements in the water, not in the sediments. Low salinity up in the river, high salinity out in the ocean, and we're along a salinity gradient here. So as we're coming down here, the conditions through which sediments are experiencing changes are such that it gets less acidic and salty, right? Just like we would expect for any estuary. Okay, so now here's a bunch of stuff down in the sediments, right? So every one of the plots on the next couple slides is going to be depth in the sediment at those 4 stations: riverward, intermediate, seaward, right? So we always go the same way across these things. So now we've got the salinity, right? Oh, it makes sense, right? It's really low up here, way upriver, not much salt in the water, not much salt, therefore, in the pore waters of the sediment. We come out over here, it gets higher and higher. It doesn't stay high. We'll talk about that in a second, right, as we go down with depth, because some of the components of the salinity, for instance, sulfate, which is one of the 4 major ions in seawater, it gets reduced as we go down with depth. So it's going to make the salinity go down a little bit, because as it gets reduced, it changes the salinity characteristics. And we see that here by looking at sulfate concentration. So up here in the river, or in the watershed, the first 2 stations, meaning this station and this station, there's no sulfide in the sediment, and there's very little sulfate because ocean water doesn't make it that far up, and the freshwater part of this ecosystem doesn't have a lot of sulfur. Okay, so we don't get sulfate. We do get sulfate as we go more downriver, the further down we go. But then as we go down with depth in the sediment, we see it consumed. Where is it consumed? Redox left. Okay, so as you can imagine, chemical phases that depend on the presence of sulfate or sulfide, the thing that is made when sulfate goes down by reduction, might be found as autogenic phases when we get out to the more oceanward part of the system, but not found here because there's no sulfate in the water, as an example of it. And this is just how pH works. Okay, so here's some more chemicals. We've got organic matter, BOC, reduced sulfur, sulfide, and dissolved organic carbon. Okay, these are a little bit, more complicated, a little bit more difficult to see, but we see that the concentration, for instance, of organic matter is, unfortunately, they didn't have any data on this thing, but it's relatively constant as we go down with depth and not that different from place to place. However, the highest organic matter anywhere is in the surface sediments upriver. Terrigenous particles carrying the legacy of, that water flowing through the watershed supplies organic rich sediments. And as we talked about with the copper last time, a lot of organic matter flocculates out in estuaries very high up away from the ocean. So it gives us high concentrations in the sediments. Now, unfortunately, as we go down with depth in the sediments, we're seeing the integrated processes of deposition as well as things that happen in the sediments due to respiration. So the concentration goes down because respiration of that organic matter decomposing some of it. Does that make sense? Okay. We also see the dissolved organic carbon content do a somewhat similar thing. And we see reduced sulfur, if anything, increasing out here. Here it's a little bit more complicated, not clear exactly what's going on, but starts out low, it does increase with depth. Sum of CO2, the total carbonate, bicarbonate, and dissolved CO2 increases in all cases, but increases more here than it does here. Okay. Why might that be? Well, we know that the CO2 reflects a bunch of things, but primarily the composition of photosynthesis and respiration. So that's largely being driven by the organic matter content in the sediment and respiration thereof. As one of the things that's happening is why it always increases with depth, because respiration is increasing with depth. But then there's also pH, right? So remember, we go from much more acidic to less acidic conditions as we go through the riverine system to the ocean, so that as we start to respire organic matter and produce CO2, because there's already calcium ions present, some of that will form calcium carbonate and come out of solution. And we can see that the effects of how that happens changes as we go from the riverward to the oceanward section, in part due to changes in pH. Now, in this diagram, we have the two nutrient elements, nitrogen as ammonia and phosphorus as, reactive phosphorus just means the forms of phosphate that are not stuck onto particles. As we've talked about before, a lot of phosphorus sticks onto the particles. And again, we see the concentrations change a little bit. They increase with depth. These things that are a part of the organic matter are liberated by respiration. The nitrogen is, the nitrogen is reduced, so it goes from nitrate to ammonium. That's part of nitrate reduction process. And the phosphorus concentration just kind of increases. Part of the reason the phosphorus concentration increases is because of liberation of phosphorus from the organic matter. Does anyone remember when we were talking about lakes? I said, oh yeah, there's this iron-rich phase that phosphorus sticks to, and a lot of phosphorus in lakes goes down into the sediments until they go eutrophic. And then a lot of that phosphorus gets liberated. It's called vivianite. It's an iron phosphate. Well, if we go into reducing conditions and we have phosphorus being liberated by our organic matter being decomposed and sticks onto particles of iron, and all of a sudden we get far enough down the redox ladder that the iron particles get decomposed, and because it turned from iron 3 into iron 2, then the phosphorus is going to get liberated. So phosphorus concentration will go up simply because the thing it was sticking to in the particles is now not a particle anymore, and so the concentration in the water will increase. So that's just an example from one place, but because of all of the kind of integrated effects that we just talked about, people have developed classification schemes to try and say something about not only in a modern estuary, but let's say you found evidence in a paleo estuary, like a braided river that's moved its location, and you find a deposit that's 1,000 years old, and you want to say, well, what were the conditions like in the past, for instance? And one of these ways of looking at authigenic phases, minerals that are produced on site, as a function of variation in conditions, especially in EH and pH, as well as the overlying water composition, fresh water, salt water, some mixture thereof, is this thing called the Burner scheme. What the Burner scheme does is it looks at what particular marker minerals might be sensitive to these three things: the EH, the pH, and the composition of the overlying water. Now, if I can find minerals that tell me something about these conditions, then I might be able to look at some sediments in a rock record that I think were formed in an estuarine environment, and say something about, well, how far from the ocean were we, or whatever else, how much organic matter was coming down, how fast were conditions changing with depth and EH, for instance. So the way the scheme looks, what it tries to do is it looks at mineralogic differences between oxic and anoxic environments for phases that can come out, authigenic phases, solubility differences of some elements, and for instance, the element iron in the presence of both carbonate and sulfide. If you recall back when we talked about EH diagrams, we had a diagram of just iron, and we had a diagram of iron in the presence of sulfur and carbon, and we saw that right around neutral pH and very low EH, we could make some other phases besides iron oxide, iron hydroxide. They were siderite, which is iron carbonate, and pyrite, which is iron sulfur. If we're in an environment where we have this stuff, we have a chance of making pyrite. But if we're in an environment where we don't have this stuff, we're not going to make any pyrite because that stuff isn't there, even if we have the iron. Same thing with the carbonate. Okay. And then, so, in essence, you also have to make some definitions in this scheme because the scheme is basically calculated on the basis of a bunch of thermodynamics, like solubility, using different concentrations, and then applying them to the environment. So they define the sort of oxidized and anoxic conditions on the basis of, for instance, an oxygen concentration of 10 to the minus 6 molar, which is about 0.5% saturation. It's really low oxygen content. We wouldn't tend to find this up in the water column, except we can find it in very extreme cases, but it's pretty rare. But down in the sediments, where there's restricted water flow and very high concentration of organic matter, we can easily get to these concentrations even lower. Okay, and so oxic conditions in this burner scheme are places where there's more oxygen than this, and anoxic conditions are places where there's less oxygen, for instance. So then you can kind of set yourself up a flow chart. Well, okay, let's just think about our sediments. It can be in places where it's sediments that formed out of fresh water, so there's not going to be much sulfur, right? Because we don't have the sulfur coming out of the ocean. There's very little of it in unperturbed terrestrial watersheds before human activities. So as we go down with depth in that kind of water column, we might see some changes in EH, but we're not going to see much change in the sulfur concentration because there's much sulfur to start with. We go down to the more oceanward condition, we're going to see big changes in sulfur, for instance. So we have two categories. We have oxic and anoxic, right, which is basically just a function of the EH and the organic matter and the redox ladder. But under anoxic, we have three categories. Sulfidic means, yeah, it's got some sulfur, right? So think about at the ocean side of things where there's sulfur in the water, sulfur to be reduced, we can make sulfide, cool. It's got to have at least 10 to the minus 6 molar for us to call it sulfidic in this particular scheme, okay? We can also have non-sulfidic, right? Meaning, yeah, it doesn't have sulfur, okay? And there's two reasons why you could not have sulfur. You could not have sulfur because it was never there, or you could not have sulfur because the sulfur was reduced from sulfate to sulfide, and then all that sulfide mixed with something else like iron or manganese to make a solid phase. And we keep going further down in the sediment, we don't see any more sulfur because it's been added to the solid phase. So that's the difference between post-oxic and methanic. Okay, so now you see a list of minerals. Okay, hematite, goethite, these are iron oxides, iron oxide hydroxide, manganese oxide type minerals, no organic matter, relatively oxidized. We go down into the anoxic sulfidic condition, pyrite, iron sulfide, marcasite, rhodochrosite, alabandite. Doesn't matter what these names are, but these are minerals, sulfide minerals that are common in a lot of environments that have sulfur. We come down here, we've got some amount of siderite, iron carbonate, but what we don't see in this list, we see silicates, but no sulfide because there wasn't any sulfide. Okay. Down here, we see slightly different minerals too. Here's that famous Vivianite that I mentioned, the iron phosphate, for instance. And so you can see this kind of key thing here. It says earlier formed sulfide minerals, meaning earlier meaning higher up in the stack. Right, we've gotten down below to the place where this stuff was already removed as it was produced, so we don't find it. So now these are just some delta G's of reaction for the formation of some of those key metals, right? So you can see them on here: pyrite, hematite, siderite, hematite, rhodochrosite, bernacite, alabandite, bernacite, etc. And these are reactions transitioning between sulfide rich and sulfide poor form, or carbonate rich, carbonate poor form. So we have both. And you can see reactions written for two sets of conditions. These are delta G's calculated from the delta G naught plus the conditions that were defined for the scheme, meaning concentration of oxygen greater than 10 to the minus 6, partial pressure of CO2 greater than 1, over here, and no sulfide, and over here in the sulfidic environment, concentration of hydrogen sulfide greater than 10 to the minus 6, partial pressure of CO2 greater than 10 to the minus 4. And so remember, when we have no negative delta G's, what does that mean, right? Delta G minus RT ln K. Think through that for yourself. Is a reaction favored or not under certain conditions? And what this is telling us is that for the conditions established here, these reactions are favored in the direction they're written. So we expect to see iron as an oxide, but not iron as a sulfide for the conditions that have been set up for oxic environments. Whereas for sulfidic environments, the same basic chemical reaction, but with different mixtures of conditions in the environment, all of a sudden pyrite is a stable form, right? So that gives us like a table of elements and minerals that we expect to find in sediments as a function of what was the overlying water and what's being happening down in the sediment column through the decomposition. And this is like a list of minerals that you can find. This is kind of works better in theory than in practice. There's stuff that happens in sediments that make things complicated. For instance, bioturbation, changes in sediment deposition pattern, etc. But there are places where you can kind of find these differences. And I wanted to kind of highlight this for you because you can now think about all the other chemicals that we were just talking about associated with particles that may change their association, whether they're dissolved or part of a particulate load or what particles they're stuck with, a function of changes with depth that also reflect all the things that these major autogenic phases reflect, which is the pH, the PCO2, the concentration of oxygen, and the concentration of sulfur. Okay. So that's that. Now for the rest of a little bit of time here, we're just going to start talking about the oceans, okay? And we'll continue, we'll talk about the oceans pretty much for the rest of the time in one way or another. We'll talk about, the carbon cycle as well, and a little bit of impacts on global climate from the perspective of oceans and marine chemistry. So we talked about this before. They're the biggest part of our hydrologic cycle. They're the main repository for liquid water on Earth. They contain a significant amount of the world's easily accessible carbon, mostly as oxidized carbon. That's where most of Earth's photosynthesis and respiration happens. Okay? It plays a significant role in regulating our climate, both in terms of heat distribution as well as how it affects the amount of greenhouse gases in our atmosphere, water, CO2, methane, etc. The ocean basins have very long histories, right? The continents are always moving around and the configurations of the oceans are changing. But when we look at the residence times of the longest, highest residence time elements in seawater, which are sodium and chloride, we can see that they are of this order. Their composition has an integrated history that goes back 100 million years. Right? Some elements don't last that long, they got shorter residence times. So obviously they're not going to tell us that kind of history. But the other kind of key thing is that, and we've talked about this before, that the rate of kind of ocean circulation which changes. It changes with stuff like glacial and interglacial cycles. It also changes with the configuration of the continents. But today, the way it seems to work, it takes something like 1,500 years to perhaps 2,000 years for deep water that's formed in the Atlantic to kind of migrate through the Pacific and come back. Okay, and we talked about this as well. We have concentration of the elements is the periodic chart and the log scale in micromoles. Some elements are high, some elements are low. One thing is pretty significantly different about the oceans than the rest of the hydrologic cycle is comparatively a lot less organic. Not everywhere. You can find places that are higher, but on average, the DOC in the ocean is a lot lower than it is in the terrestrial part of the hydrologic cycle. And the POC tends to continually be settling out, so we also don't see as much as high POC, especially when we get away from the coastlines. A little bit different at the coastlines where we've got continuous supply of particles, but so we don't have as much opportunity for this complexation chelation thing to happen. All right, I expect you to be able to follow this table here. I want you to look at it at your leisure. There's every element in the periodic chart. It's concentration in streams, it's concentration in seawater. And until hydrothermal vents were discovered, people used to think about the concentration of elements in seawater as largely reflecting the flux in from the stream or river flux, plus something that happens at depth to cause things to sediment out. We now know it's a little bit more complicated than that. We've got hydrothermal circulation. We've got supply of elements in the dust flux that adds stuff to the center of the ocean. So the residence times, mean ocean residence time is mort, but it's also just the residence time of all these elements. And you can see here's some long ones. Here's sodium, 2 times 10 to the 8th, right? That's 200 million years. That's a long one. We got some short ones. You know, here's iron, 6.9 times 10 to the minus 1, less than a year. There's a huge variation there. Okay, and those can be calculated. You can calculate them yourselves. Calculate residence time by taking the reservoir and the flux in, and assuming this is just the flux, you can divide one by the other and come up with these numbers. These are enrichment factors. Some elements are enriched in seawater relative to freshwater part of the hydrologic cycle. Here's one that's really big, bromine. Some are depleted, right? Lower in the oceans than they are in the freshwater. Okay, and now you can see these 4 categories, classification, 1, 2, 3, and 4. Okay, so category 1 are conservative elements. They all have long residence times. These are things that basically spend a lot of time. You can see it down here. And all these others are non-conservative. Okay, category 2, 3, and 4 are non-conservative. And you can be non-conservative for 2 main reasons as an element. You're non-conservative because you're tied up in the cycle of life, photosynthesis, respiration. Or you can be non-conservative because of some other thing, like your chemical solubility is a function of things like pH or pressure or temperature. Okay, and you can be non-conservative because we don't know. That's what category 4 is. We know it's not conservative. We see lots of variation. We see short residence time, but it's not known if it's due to life or not. In category 3, it's definitely not due to life. In category 2, it definitely is due to life. So if you remember back when we talked about conservative ions or things that are insensitive to changes in pH and temperature and pressure, what we expect for those elements which happen to have long residence time is that the ratios in seawater are going to be constant throughout the oceans because the oceans are well mixed, even if the absolute concentration of any elements is different, right? Like if you go into the surface oceans, you're in a place where it rains a lot, the salinity of the water is going to be lower than if you're in a place where it evaporates a lot, where the salinity is higher. But the ratio of any 2 elements, like the ratio of sodium to chlorine, will stay the same because they're conservative. So conservative elements have constant ratios. Non-conservative elements don't have constant ratios. That's how we define it. Okay. Now we've talked about a lot of these phenomena already, but I just kind of want to remind you of, for instance, if we want to do some kind of model that tells us how do the ocean compositions develop and how do they evolve over time, we need to look at the fluxes in and out. The fluxes in include stuff that comes in at the top of the ocean, right? Rivers, precipitation, dry deposition of particles, gas exchange, and stuff that happens on the bottom, which is primarily seafloor volcanism, interaction of water with the crust. Then we've got chemical fluxes of things out of seawater. They include gas exchanges happening to the surface, formation of aerosols and particulates that, for instance, form marine rain, And sedimentation, which accumulates at the bottom of the ocean, and alteration of the basaltic oceanic crust. There are some other ones as well, but these are the main ones, right? Now, also think about the fact that the oceans are stratified, like a lot of parts of the hydrologic cycle, the holding tanks, okay? And so we have stuff being fed into the surface ocean. That's what this stuff is, stuff coming back out. We have this separation across a thermocline to the stratified part of the ocean, the deep water masses, right? So the fluxes that happen here on the bottom due to volcanism, they affect bottom water. They don't affect surface water as much, right? Because these two parcels of water are largely isolated. And the stuff that affects the surface ocean largely affects just the surface ocean and not the deep water. We can find a zone of mixing in between them, right? Compositional mixing, but the bulk of the oceans really operate as two separate reservoirs, surface and deep. However, there are places in the ocean basins where currents can cause water to go from the surface down. These are the places where deep water is formed, the North Atlantic and the South Atlantic. We've talked about before, and places where upwelling happens. And when the upwelling can take place in a lot of different ways, it can be a very kind of diffuse, broad-based pattern of return flow, such as happens throughout the North Pacific along the transit of the oceanic conveyor belt, or it can be places where there's a focused flow. And one of the key things that about focused flow upwelling is it takes compositions from down here, which have the legacy of respiration over photosynthesis, so they have a lot of free nutrient concentration and relatively low oxygen, push them back up into the photozone and can fertilize things and cause really dramatic effects. Okay. So conservative elements are well mixed in the oceans. Even if their concentrations differ, their relative concentrations don't. Ratio. Non-conservative elements can be dominated by biological processes, which are photosynthesis respiration, or not. Okay, most photosynthesis respiration in the oceans has that Redfield ratio kind of composition, as we've talked about multiple times before. The next few slides, just talk about some of the physical characteristics of seawater. Like what is the salt content, right? We've talked about ionic strength before, and ionic strength of seawater is about 0.35. Typical seawater salinities in the open ocean go between about 33 or so to 35.5. You can find higher values. You go on the Mediterranean Sea, it can be up over 36, for instance. But these are typical values. Okay, and the ratios of the elements that make up most of the salinity are constant. These are a couple of other kind of relationships. I've mentioned before chlorinity, right? We used it in the estuaries last time. Chlorinity is just the chlorine part of the salinity. And this is just the relationship between salinity and chlorinity. It's just an equation. Because the ratio in the oceans of sodium to chlorine is constant, and sodium to the other major constituents of salinity, such as magnesium and sulfur, is constant, we can write a simple equation. And the reason why people do this in part is because this is really easy to measure. This is a silver nitrate precipitation of chloride. They could do this, back hundreds of years ago. Just add dropwise a certain solution of silver nitrate, which is soluble. It mixes, quantitatively with the chloride, precipitates out silver chloride. You can filter it out, dry it, weigh it, or whatever. Nowadays, you use electronic instrumentation. This is one of the reasons why people fuss about salinity. It's not exact because the other halogens in water, the fluorine, the bromine, the iodine, they're also going to mix with this. But these are kind of very small details. So there's one other thing which I put on here for as an effective salinity. We all know that when you add salt to water, you depress the freezing point, right? Remember that freezing point depression, right? You can calculate how much the freezing point depression is for typical seawater, writing out the equation for how it is calculated. And depending on, I have a couple of examples in here on this slide, the next slide, you can assume that all the salinity in seawater is just sodium chloride. In which case you can convert the salinity of 35 to 0.6 mole. Or you can say, oh no, it's got a proportion of sodium and a proportion of magnesium sulfate and whatever. And so, but the key thing is that for a typical estimate of the composition of seawater, you come up with a temperature depression, freezing point depression of about a degree. And this ends up being really important in things like sea ice formation, how that varied over time, If the oceans were a lot saltier, then they would freeze a lot less on their surface. If they were less salty, they freeze more. And so, part of the overall cycle of, climate and everything else is affected by it. So, we'll stop it here, and then the rest of this stuff I'll add into, next time on Tuesday. Questions? All right. So be looking for that homework 3, and I'll do the official